All right, in this next problem, we just want to find the KEQ of this and of this equation here. So it's nothing really different than what we've done before. So KEQ is equal to the products raised to their exponent. So here's our SO3. Raised to their coefficient, raised to the second power, over our SO2 raised to the second power, and our O2 raised to the first power. All of those gases are our gases, so we don't have to worry about ignoring them. And we've got heat, so it's not going to come into play to writing our KEQ. So if we look at this equation, we want to see how we can get this reaction to shift in response to these following stressors. So we're going to add more oxygen. We're adding more reactant, so it's going to shift it to the right. And if we remove some SO2, it's going to shift it back to the left to kind of fill up that void. If we increase the pressures, if we increase the temperature, in this case temperature heats on our reactant side. So if we increase something on our reactant side, we're going to shift it towards the product side. Reverse everything I just said there. Heat is on the product side. If we increase something on our product side, it's going to shift it to the reactant side. Here we're going to increase pressure, so what we have to look at is the total number of moles on each side. We've got 3 moles here. We only have 2 moles here, so in situations where we have high pressure or low volume, we're going to shift it to the side with the less number of moles. So if we increase the volume, we're going to shift it towards more moles, and that just goes right back to our coefficients out there. If we add some more SO2, we're adding reactant, so it's going to shift it to the right. If we add a catalyst, all catalysts do is increase the rate of the reaction. They're not used up in that, so anytime we have a catalyst in an equilibrium, it's not going to change. No shift, no change. If we decrease our temperature, that's the same as removing one of the products, so it's going to shift to the right. And then if we remove some SO3, that's also one of the reactant or products. So if we remove some of the products, it's going to decrease their concentration. It's going to move this equilibrium to the right. Now if we go down here, this is a different way to approach one of these K problems. So we have a K value for a reaction from number 7. So I give you the KEQ, and that's going to be 0.260. At special temperatures and the equilibrium concentrations for the rest of them are known. I want to find my concentration of SO3. So KEQ is equal to SO3 squared. I'm just copying down what we had for number 7. SO2 squared and our O2. I'm given KEQ, so that's and then now what I'm looking for is the equilibrium concentration of SO3. So how would I get SO3 all by itself? Well, I'm just going to multiply each side by SO2 squared and O2 squared. There we go. SO2 squared, O2, and that's going to equal SO3 squared. How do we undo a squared? Well, we got to take the square root of this, which means I've got to take the square root of that answer there. So now SO3's concentration is going to equal to the square root of 0.260. These are just from the problem. 0.250 squared and 0.375. If I do this math, I find that the concentration of SO3 is going to be 0.0781 molar. And then the very last problem I don't have on this page right here, but it says discuss the instances when a change in pressure on a system or equilibrium will have no effect on the concentration. If we change our pressure and we've got equal moles of product and reactant, well, there's nowhere for the equilibrium to go. So one side is in favor of the other. So anytime we have a change in pressure and we have equal moles on both sides of our equilibrium, we're going to have no shift in our system.